Welcome everyone for our first in-person stargazing lecture exactly. It's very exciting. We haven't had one of these since February of 2020, and we're starting to do these again. So thank you all for being here, and thank you live remote audience who's joining us from around the world. Pleasure to spend Friday night with you. Just a couple of announcements before we get started. A rough schedule for tonight. I'll spend 2 more minutes giving announcements, and then I'll introduce our speaker for the evening, who will give a talk about neutron stars, really interesting objects in the universe that we don't. Well, I'm going to learn a lot more about them tonight than I already know, and then after that, we'll have telescopes set up on the field. Right now, the sun just set a few minutes ago, so we're waiting for it to get dark enough to actually be able to see targets in the sky. But we have a number of telescopes set up looking at different astronomical targets, and we'll also do a live Q&A panel consisting of different members in the department to answer questions about whatever you may have about astronomy or physics or science and space science. These events happen one Friday a month, and our next one will be happening roughly a month from now, given by Janusz Dewberry, about planet quakes, not just earthquakes, but using seismic waves inside the interiors of other planets like Jupiter and Saturn to figure out what's going on in their interiors. That should be pretty interesting, so stay tuned for that. We also have a sister series of events called Astronomy on Tap that are traditionally held in a bar and given 2 informal talks given by different scientists about their research, and then there's pub trivia, and it's all fun and games. Those are one Monday a month. Our next one is a week from this Monday on the 23rd. It sadly will not yet be in person. That'll be only available over YouTube and Facebook Live and so on and so forth. But the talks will be the science of Star Trek and the science of Star Wars. One speaker is going to be Michael Wong, who is a postdoc at the Carnegie Institute. The other speaker, sadly, is going to be me. So hopefully I'll live up to Michael's excellent knowledge of Star Trek, and I'll try and do some research on Star Wars. I mean, I love Star Wars, but I'll try and step up my game. Anyway, yeah, I guess those are the main announcements. As everyone is, you have to remain masked while we're in here. That's just Caltech policy. But thank you for abiding by that while you're here. And I guess those are my major announcements. So our speaker for tonight is esteemed Professor Katerina Chatziioannou, who is an assistant professor in physics here at Caltech, and focuses her research on the study of gravity and the impact that has in the strong force, or the strong realm of gravity in proximity to neutron stars and proximity to black holes. And she's going to talk about some of that with us tonight. So please welcome Professor Katerina Chatziioannou. Thank you so much for joining us.
Yeah, thank you. So I'm part of my life, and I'm speaking when I take a mask off again. Policy. Yeah, thank you very much for being here. About almost a year ago, I gave the first in-person colloquium in the Caltech Astro department. So I guess a year later, it's fitting that we also have the first in-person astrogazing talk. Okay, so I will talk today about neutron stars, and I have a bit of a complicated title, this extreme matter, extreme gravity, and I'm going to explain why all this happens in neutron stars, what neutron stars are, and why they are so exciting. So to talk about, to understand neutron stars, we begin by just considering what happens to stars. Stars, like our sun, do not stay in that stage forever. They eventually will burn all the fuel at their course and will continue changing and transforming into different kinds of celestial objects. And in this sort of complicated diagram of the various stages stars go through, you might be a bit disappointed to find out that our sun would fall into what we call an average star. It's not a very extraordinary star. It's a pretty average one. But once it burns all its fuel, it will continue evolving to a red giant nebula, and eventually what will be left of it at the center will form what we call a white dwarf. So this is sort of one of the possibilities of what can happen after stars have exhausted all the fuel and move on from their normal lives. But more exciting than our sun, perhaps no offense to our sun, we like it, if you have more massive stars, of which there are a lot in the universe, you can have more spectacular things going on, including at some point a supernova explosion, which is what it sounds, it's an explosion, where the star just releases a lot of its mass out in the universe. And then what remains at the center, again, collapses into either neutron stars or black holes. So these are the most kind of extreme objects you can have at the end of the life cycle of stars. You can have white dwarfs, this is what our sun will do, but we also can have more extreme objects like neutron stars and black holes. And the thing about all these objects is they are the end stage of stars, but also when we think about stars and our sun and everything else in galaxies, what happens in the universe, all things are massive. These are very big structures. The kind of stars we're talking about here at the end of the white dwarfs and neutron stars are actually not that big, at least in terms of astronomical quantity. So here's this actually to scale, as much to scale as it can possible. So take the same amount of mass and put it in different kind of objects to see how big they will end up being. On the left, you have the sun. You can't really fit the sun into a slide like this scale. You kind of see its surface a little bit on the side. In the center, that would be a white dwarf. Its size is roughly the same as the Earth's size. So the radius is a few thousand kilometers, a few thousand miles. So it's still a kind of big object, looks somewhat like our Earth. Compared to that, a neutron star will be the purple thing, the purple little thing on the second to last object. So it still has an enormous amount of mass. It has the same amount of mass as our sun, or maybe even more, but its size is actually very, very small. And if you can see it, I hope you can see the kind of dashed line at the end, that's supposed to depict a black hole. Black holes, get back to this, they're sort of time characteristics that they emit no light, so you can't even see them, so we kind of draw some lines to try to depict how big they're going to be. So these are small objects in size. They have a lot of mass, but they are small in size, which means you can actually do fun comparisons like this. This is what a neutron star looks like if you artificially suspend it over, you might recognize a map. This is Los Angeles. This is what a neutron star would look like over Pasadena. For comparison, here's a black hole. It would look, well, slightly smaller, but not that much smaller. So we're talking about very weird objects. We're talking about objects that have a lot of mass, but in a very small amount of space. And this is where the first thing that's extraordinary about neutron stars comes from. Their extreme gravity. Because they are so small, pretty much like black holes, the gravitational interactions and the gravitational phenomena they experience are actually some of the strongest and most violent possible in the universe. So let's look at this. Let's talk a little bit more about what kind of objects there are that undergo these extreme gravitational interactions and what those things look like. So again, hopefully to scale as much as I could to draw things scale and slide. On the left, you have a neutron star. On the right, you have a black hole. So these two would have something like 1 times 2 times the mass of our sun. So think about 2 times the mass of our sun, packing it down to objects that have a radius of about 12 kilometers, which I think is something like 6 to 7 miles. Or in the case of black hole, a slightly smaller radius of about 6 kilometers. So you have those very big objects in terms of size, in terms of mass, very small in terms of size, and they're out in space. So outside those objects would have vacuum, they're sitting in space. But then as you get closer and closer to them, weird things start happening because of gravity. So on the one hand, you have black holes. Black holes are fascinating objects because they do something very counterintuitive for us, for our sort of daily lives. They have this dashed line depicting an area around them that we call an event horizon. What an event horizon means is that if you're inside this region, if you're inside the dashed line, then nothing can escape, not even light. And that's not something we really have a lot of intuition from our daily lives. But because of the extreme gravitational conditions around the black hole, not even light can escape. That's what we call the event horizon. But nothing really weird happens at the event horizon other than light cannot escape. When you fall into a black hole, when you cross the event horizon, you would actually not understand anything happening. There's nothing weird happening at the event horizon versus a little bit further out. So both inside and outside this event horizon, you just have vacuum, you have nothing, you don't have any matter. Neutron stars, on the other hand, this is where the exciting stuff begins. They have a physical surface, just like the Earth, the surface of the Earth, when you can't fall in, or any other kind of object we know of in our daily life. There's a surface that you cannot penetrate. And inside that, you have just material, just normal material that you know of from everyday life. So this is the sort of situation. This is why neutron stars have this, what we call extreme gravity, because they are so small that we basically, for some aspects of them, behave like black holes. So as you go to the center of this kind of objects, gravitational fields get stronger and stronger and stronger. And at some point, unfortunately, even for black holes, we reach a point where we don't fully understand what's going on at the center. So we understand extreme gravity and this kind of objects, how they behave. We understand them through Einstein's theory of general relativity. And unfortunately, as we go to the center of those of black holes, we hit some singularities in the theory, and we think that probably the theory breaks down. We don't fully understand what is going on. And excitingly, the same kind of thing happens for neutron stars, but for slightly different reasons. As you go closer and closer to the center, you encounter more weird and weirder forms of matter that you somehow do not fully understand at this point. And that's where the second aspect comes in. This is the aspect of extreme matter. Besides extreme gravity inside neutron stars, we also have extreme matter. So let's think about matter, what matter is and what's sort of the normal matter around us. Most of the matter around us is made of atoms. They have a nucleus at the center and electrons going around. And interactions between those different atoms form the everyday matter around us. And that sort of happens in neutron stars, but at the very outer layers of the star. So here is a sort of artist's impression of a cross-section of a neutron star. So imagine you take a slice out of it and look what happens inside as you go inside the star. And in the very outer layers, matter doesn't look too different from what we sort of experience in our everyday lives. But as you go close,
Sorry, we're having trouble hearing you on the phone, and I've got maybe a few.
yeah.
Sorry, guys. Technical difficulties.
Sorry. Okay, so let's try this. A little bit closer.
Yes.
Let me know if there's still a problem.
Thank you very much. Sorry about it.
Yeah, no problem. So your first time trying all that. Okay, so we're talking about extreme matter inside neutron stars and how matter, because it's so packed together, we're talking about a huge amount of matter packed together in a tiny object. Because it's so packed together, it starts looking different than the normal matter we encounter in our everyday life. In the outer layers, it kind of looks similar. We have our atoms, our nuclei, but as you go closer and closer together, those kind of clean structures you expect to disappear. So what happens if you have two atoms and bring them very close together? The outer layers of the atom will start sort of overlapping with each other. And eventually, if you bring them very close together, you don't know where one atom ends and another atom begins. So they're sort of one. And if you keep packing them closer and closer together, you will end up with a situation where even the nuclei, the very nuclei of the atoms, are so close together, they start interacting with each other. You pack them closer and closer together, and they start overlapping. You start losing track of which nucleus is which because they are so close together. This is what is happening with neutron stars. The nuclei are packed so close together, you can't tell apart individual atoms. You can't tell apart individual nuclei as you go to the center. Nuclei are made of neutrons and protons. These are some of the kind of particles that we consider a lot when we talk about our everyday matter. And if you keep packing them closer and closer together, at first, you start with individual neutrons and protons that you can pinpoint. But if you pack them close and close together, you start losing track again of which neutron is which and which proton is which, because they're so close together. This is what happens all the way at the very cores of neutron stars. Matter is so packed together that you can no longer easily tell apart which particle is which and which particle does exactly what. And this is sort of a regime where we can't fully calculate what is going on. We can't fully observe with today's capabilities what is going on. And you might sort of see it on the bottom right, is where the question marks start appearing when we write down what could possibly be happening inside neutron stars. All the question marks means that we start not being entirely sure what is going on, because matter is pushed to such extreme conditions that we don't have either theoretical calculations that can help us here, or any experiments here on Earth, anything we could do on Earth to understand what is going on. Okay, so neutron stars, of course, are kind of common objects in astronomy. Famously, they're full actually positive. I'm not sure how comfortable it is having that thing flashing in front of me. So, so famously, the existence of neutron stars was predicted theoretically before they were observed by astronomers. But today we've observed a lot of such neutron stars with something, a phenomenon that is very similar to how a lighthouse operates. And neutron stars emit radiation from distinct points on the surface of the star. And I'm going to start for just a little bit, I promise. But as the star rotates around some spin axis, at some point, this sort of radiation passes through Earth, and you detect it. And we detect it mostly with our radio telescopes. Here is an example of such a radio telescope that's a Greenback Observatory in West Virginia that emits those pulses of radiation every time the lighthouse beam passes through Earth. And this is how we have so far been detecting neutron stars. We detected a lot of them in our galaxy. Okay, so this is sort of the general picture for neutron stars. But going back to the issue of extreme gravity, there's another way we can detect neutron stars with and understand them, and that's gravitational waves. Gravitational waves were detected for the very first time in September 14 of 2015. The discovery was awarded with a Nobel Prize in Physics a few years later. And the very first observation that was made in 2015 actually came almost very well aligned with the 100-year anniversary of general relativity. So Albert Einstein proposed general relativity in 1915, and about 100 years later, gravitational waves were observed for the first time. And we have those beautiful signals that you might have seen from other astrogazing talks or general popular computer science. So to understand a little bit gravitational waves and what they can do for us, for neutron stars, how they relate to neutron stars, we need to talk a little bit about general relativity, unfortunately, or fortunately, if you like. So we need to talk a little bit about gravity. Most of our, when we are trying to understand gravity, most of our year we spend thinking of gravity as another force. Another force in our universe, same way you have common forces when you push something, or when you have two charges, they exert an electromagnetic force with each other. So people thought, well, why not gravity doing the exact same thing, right? You have two bodies with two masses, and they exert a force on each other, and that's the gravitational attraction. If the two bodies is the Earth and me, this is what keeps me on the surface of the Earth. And that theory worked perfectly for a very long time. Newton proposed it centuries ago, and explains essentially all phenomena on Earth and almost everything in the solar system. But cracks started appearing in the picture sometime in the 19th century, and they were both conceptual cracks, but also experimental. There was some observational. There was some observational evidence from the trajectories of bodies in our solar system saying that this sort of picture was probably not correct, or at least it wasn't 100% accurate, which is when general relativity comes in. And Albert Einstein substituted this beautiful, simple equation that tells you what the force is between two bodies given their mass, with an equation at the top, which I'm not going to go in because it is about 100 times more complicated to even understand. But the idea, the conceptual change here is that gravity is no longer a force like two objects exert on each other, but instead it is a manifestation of something we call space-time. So space-time is the concept of some sort of structure that covers the entire space and time. And every object in our universe curves this structure, curves this space-time. So here's sort of a depiction of what the sun would be. And the surface under the sun, if the sun was not there, it would be flat, so your space-time would be flat. But the presence of the sun causes the surface. The presence of the sun causes the surface to curve. And that depicts the space-time around the sun. So then the Earth, when the Earth moves around the sun, rather than doing this because the sun exerts a force on the Earth, it does it just because it moves on this curved space-time. If you think as sort of a trampoline that is curved, or an object moving on a trampoline, they would follow a trajectory that is quite similar to how the Earth goes around the sun. And that's just because the Earth, as we sort of think about this concept today, the Earth moves on a curved space-time. So once you have this sort of picture in your head, that space and time together form this structure we call space-time, and everything happens on this curved space-time, this is where you can understand gravitational waves. Because this space-time, if you can curve it, you can also change it. You can sort of shake it, you can wiggle it, you can do whatever you want to it. And that's exactly what gravitational waves are. When this sort of space-time starts changing with time, quite violently. The picture is kind of similar to this. If you have some surface of water and you draw something on it, you'll start getting ripples on your surface. In this case, what we for gravitational waves, rather than something falling on the surface of the water, I don't know if you can see it very well here on the left, that depicts two black holes that orbit around each other and eventually collide. And this is what causes those ripples on this nice surface. So this is what essentially gravitational waves are. Space-time, Einstein introduced the concept of space-time. Objects curve space-time, and certain things can also not just curve space-time, but also change its structure with time and wiggle it around. And this wiggling is what gravitational waves are. Okay, so what do? Gravitational waves propagate out in the universe. They're everywhere in our universe, including here right now. They're just very weak that we can't detect them. And what do? So they wiggle space-time. That's what they do. And space-time means space. So where we exist, where we live, the distance between us. And all that structure wiggles. So because of this, that means that the space between me and you changes. So either it gets stretched or gets squished or moves in other ways. So this is, I'm gonna show you an animation of what would happen if a gravitational wave passed through Earth, and you see how the Earth wiggles around. And before anybody says this in panic, I should say that the effect is vastly exaggerated, just because you need to be able to see it. Nothing of that sort of magnitude actually happens, but you see sort of the wave passing around and the Earth starts wiggling. And the stronger the wave, the more violent the wiggling. And then the wave is gone, and then the Earth returns to its original shape. Nothing like that really happens of that magnitude. It's impossible to make a wave strong enough, so don't panic, we're not going to break the Earth. What we actually, the effect we actually try to observe gravitational waves is millions and billions of times less strong than this. But this is sort of the basic idea. Gravitational waves pass through Earth and they wiggle everything around us. Okay. So then we detect black holes with this, and black holes are the best kind of object for this sort of business because they are the most extreme gravitational object we have. They are basically pure vacuum, pure curved space-time that just exists there without any matter, without any other structure. So what we first observed with gravitational waves was two black holes that collided. So let's play a simulation of this. You will see two black holes here. These are the black, as you can probably guess. And they orbit around each other. And you see this nice image is created because the black holes have been artificially placed in front of a field of stars. And reality, we don't do that. It's just for a little bit of exaggeration. So let's actually sort of play again. So what happens again when stars playing is the two black holes orbit around each other the same way the Earth orbits around the sun. But unlike the Earth and the sun, those black holes progressively get closer and closer together. So when the Earth orbits around the sun, it fills in, it moves in a almost circular motion and comes back to sort of the same position, and then does again and again and again and again. It doesn't go close to the sun. It doesn't fall in the sun, thankfully. Those two black holes fell into each other. So what happens is that because of the gravitational waves actually remove the energy from the system. The system loses its energy. This is the same sort of thing you have if you roll a pencil on a table. Friction will cause it to eventually stop because friction takes its energy. This is the same thing that happens here. Gravitational waves take away the energy from the system. So the two black holes get closer and closer together until eventually they get so close together that the two black regions depicting the event horizon sort of peacefully come together and merge into one. This is the same sort of picture we're talking about neutrons and nuclei earlier. If you get them so close together, eventually you lose track of which one is which. So the black holes here, you get them so close together, and then they just join into one. They will do it about now. And you have just one black hole at the end. Neutron stars can do the exact same stuff. Because, again, you have extreme gravity operating around neutron stars, they will do sort of the same thing. And we observed that on August 17, 2017. I'm going to show you another simulation of what happens when the two neutron stars undergo a similar kind of dance and get closer and closer together. And let's see what happens when they do that. Because something slightly more exciting will happen. So we have two neutron stars now. Those are the blue circles here. They orbit around each other, they get closer and closer together, but they can't peacefully merge anymore because they have physical surfaces. The two physical surfaces will collide with each other, and the whole thing will be a complete mess. All the color you see around this is matter. This is like a violent collision it's going to play again, where you have two balls of matter, you collide them with each other at very high speed. What will happen is debris will fly all over the place. This is what neutron stars do. They travel in this sort of interactions at very large velocities, fractions the speed of light, and they collide so violently that they just eject debris all over the place. And this is the kind of things that we want to understand. And to understand this a little bit more, what kind of things matter does for you, let's go back to talk a little bit about the Earth. I'm going to take a little bit of inspiration from the Earth again to see what happens with neutron stars when they collide with each other. So that's another picture of a neutron star, this time not placed over Los Angeles, but placed over my hometown. That is in Greece. So down here, this is Athens, enclosed by the mountains. I'm guessing this is the airport. Looks like an airport. And if you drive about an hour north of Athens, you will get to an island. This is a very long, skinny island called Egea, which is where I grew up. And here's a neutron star placed over my hometown. But the reason I'm telling this story is not because I'm going there next week for the first time after 3 years, and I'm very excited, because the island is very close to the mainland. You sort of see the little road there, and they're so close together that there's a drawbridge, and which makes traveling very easy and very convenient for us. And under the drawbridge, this is what happens. This is a video. The sea, the water under the bridge flows and flows quite rapidly. And it doesn't flow in just one direction. 6 hours of the day flows from north to south, and then it reverses in direction. And for 6 hours, it flows from south to north. What kind of physical effect is this? What, on the surface of the Earth, what kind of effect causes such large bulk motions of seawater? Any ideas?
Tides.
That's tides. Exactly. So these are tides caused by the moon. And by the way, there is I don't think it's true. I don't think anyone thinks it's true, but there's a sort of legend that Aristotle was trying to explain this phenomenon and couldn't, and fell in the water and drowned. I don't think it's true. But that's the sort of legend. But it's a very weird phenomenon. Imagine being in a place in the water, change direction every 6 hours, and you don't know what's going on. So this is tides. This is the moon. As the moon moves around the Earth, it pulls the water, pulls the Earth's water, and the water just moves around, and that causes things like the water level rising and lowering, tides going in and out. And the exact same thing is what happens with neutron stars. Now you no longer have the moon and the Earth, but you have two neutron stars. And as they get closer and closer together, there is tides on each other. So this is a kind of quite spectacular phenomenon that the combination of extreme matter and extreme gravity can do for you. With gravitational waves that are given to us by extreme gravity, we can measure tides. We can measure this sort of tidal motion on not the Earth, but on neutron stars and objects that are not bigger than Los Angeles, and are 100 million light years away. And that's what extreme matter does for you, causes those large tidal motions. So this is why neutron stars are so exciting. This is why they're a combination of extreme gravity and extreme matter. And of course, there's a lot of stuff going on with neutron stars, more than I can talk about today, but because there's matter, there's debris flying all over the place. When you have collisions of neutron stars, it's not just gravitational wave you can observe them with, but you can also observe them the same way you observe everything else in the universe with electromagnetic radiation. So the very first binary neutron star merger we observed back in 2017 was observed not just with gravitational waves, which is those ripples in space-time caused by the motion of the stars, but was also observed with electromagnetic radiation almost across the entire spectrum. This is when the two neutron stars collided. All the debris that flew all over the place emitted more light and was observed with, for example, invisible infrared, radio waves, X-rays. Could have happened with neutrino, but it actually happened. It was possible without us to do it, but something for the future to look forward to. There's more interesting and exciting stuff happening during this sort of observation of the same event with every kind of observatory, almost every kind of observatory you can possibly think of that I don't really have time to talk about. That's a story for another day. So I will conclude here then with another nice, this is an artist impression of the collision of these two neutron stars. You kind of, I'm not 100% sure what it shows, but I think this is one neutron star and the other is here. And I'm not sure what the colors are, but it's very beautiful. So I use it regardless. And we actually observed this event, so I'm going to use it regardless. All right. Any questions? Thank you.
Questions from the audience? We have a number of questions online as well that I can ask of you, but I think priority should go to the people who show their pictures.
So when do we expect the next thing like this to happen?
Yeah. Yes. So the question is when we expect the next thing like this to happen. And in this sort of picture, when you have one object and you observe it with as many observers you can possibly construct, at least for this particular event, the instigator was the gravitational waves. This was the first signal you detected, and then we alerted everyone else to look at this event and told them where to look. So hopefully the next time this will happen will be the next time we observe gravitational waves from another event like this one. And that is not going to happen until at least December. And the reason is simply that our detectors are not currently operating. So our detectors go through cycles of upgrades, we need to fix them, and then we need to take them online again, we start operating and we take data. And unfortunately, the pandemic has sort of delayed this cycle of upgrades and running. And the next time that it will continue taking data, commencing data again, will be in December 2022. So hopefully December 1st, 2022, I would say.
Is it possible for neutron stars to collide and form a black hole?
Yes, excellent question. Yes. So is it possible for neutron stars to collide and form a black hole? Yes, they actually can. And funny enough, this is what this simulation does at the end, though it's got this. So it's actually like the whole thing. So you can see it. I started a little bit closer so we can play multiple times. But in this particular case, the two neutron stars will come together, they will collide, emit stuff all over the place. And at the end, you still have a central object that is very dense. It looks like a neutron star. It survives for a little bit. It tries to stabilize itself. It's very, oh, no. Yes, definitely it is. There you go. Tries to stabilize itself as much as it can, and then it just can't do it and gives up and collapses to a black hole. So this is most likely what's happening. We're not 100% sure, but most likely this is exactly what's happening in most of those cases. And we hope with more data to actually confirm it.
I have a question from the internet. May I borrow the mic just so I can check this correctly? So I'm just going to take a couple of questions from people who are watching the live stream. Stephen Schreier and Meghna Varma both ask, at some point as black holes merge, their event horizons make contact. Is there any possibility that radiation or matter might momentarily be ejected from merging black holes, or is that just the gravitational waves that we're seeing? Is there any normal radiation or matter that might sneak out during that messy collision?
Yeah, so unfortunately, normal radiation, ultraviolet radiation, can only be emitted by matter. So photons are emitted mostly by matter. So unless you have actual material around the black holes to emit the photons, just two black holes on their own, we're not going to do it. The collision of two black holes, it's kind of a weird thing. It's actually a collision of vacuum against vacuum. And despite that, it's so spectacular because that vacuum is so highly curved, space-time around it. But this vacuum is so highly curved. But there is no actual matter. Let me stop this. Not all dizzy, but it's military. So unfortunately, you don't have any matter. Now, you can come up with other ideas for what you can do. Maybe have some relative matter around the black hole that could do this, or you can have magnetic fields. But all of these are hard scenarios to really think how they could occur. And this is a good point where observation can help us if we actually see an event like this, where you have a gravitational wave from two black holes that collide, and then you see some photons. That would, first of all, be extremely exciting, and second, would cause a lot of speculation and ideas for how to possibly conjure that. But the canonical scenario says that you don't have any photons from two black holes colliding.
Another related question.
The online audience is very busy with questions, so I'll try and refer a few of those here. One is from the nerdy walker who asks, how does the merger of two neutron stars differ from that of a neutron star from a black hole, especially at the atomic or subatomic scales?
Yeah, very good question. So you have two black holes and two neutron stars, why not have one and one? And you can totally have one and one, and we have actually observed such an event. So when you have two black holes, when you have one neutron star and one black hole, what happens is kind of similar to when an object falls into the black hole. So when something falls into the black hole, it crosses the event horizon. After it crosses the event horizon, it's kind of gone. There's nothing we can do about it. There's no way to communicate with it. There's no way for it to send us anything. And when I say it can't send us anything, we usually say that photons cannot escape from inside the black hole, but that's actually true for gravitational waves as well. If you have an object, it crosses the event horizon, if you try to send gravitational waves out to you, it cannot. They're not going to come out. The same way that photons are not going to come out, gravitational waves will also come out. So when you have a neutron star and a black hole, the neutron star will do the same kind of dance around each other, emit gravitational waves, and eventually the neutron star will fall into the black hole. And there, it is possible to still get some interesting phenomena related to matter. It depends a lot on what kind of neutron stars you have and what kind of black holes you have. But yes, this is another kind of scenario system where you can learn something about the matter, the extreme matters of neutron stars from such a signal.
I'll try. We won't go on forever, I promise, but there's some really interesting ones. Andrew Redemeyer asks, I read an old science fiction book called Dragon's Age, which was about the evolution of a life form on the surface of a neutron star. Could one neutron star cool down enough for this scenario to be possible?
Cool down? Was your
Yeah.
question, could it cool down? Yes. I mean, so the temperature of neutron stars, something like a few thousand Kelvin, which is not that high. I can imagine some life form. It's not the temperature I'm worried about, it's the gravitational field. Like whatever, if you're in a neutron star, the gravitational field is so strong, you basically be squished down like a pancake. So it is possible. I would say it's probably easier for some organism to develop resistance to high temperature than resistant to being a pancake. Possible.
So could water exist on top of a neutron star?
Could water exist? No. So you can't have structures, but you can have complicated molecules like this. Yeah.
Just crush.
Everything gets crushed. You still have hydrogen and possibly helium, but because of the pool, the only thing you can have on the surface is hydrogen because the lights. Everything else will just sink down.
Cool. Unless there are any other questions, I think we'll call it there. So please thank our speaker again. Thank you very much. Okay, so what is going to happen right now is the telescopes, the gate to the North Fields is being opened, and we have telescopes set up out there. And in a few moments, we'll set up a panel Q&A here for those of you who want to stick around and ask questions about anything related to astronomy, anything related to physics, space science, including our online audience. Unfortunately, we can't bring you out to the telescopes so that you can see through the telescopes. Maybe I'll get that level of technology for next time, but unfortunately, I don't have it for today. But we'll have a Q&A panel, and so especially online audience, I encourage you to ask your questions through the online interface, and we'll address our panel. So we'll have that set up in the next 5 or 10 minutes. And we'll keep going for another hour or so. So thanks everyone for the wonderful presentation.
Yeah.
There were a few moments. There were like, what we were just doing. We'll set up a thing here and you'll be answering all sorts of questions. What was good?
Oh, yeah.
Yeah, wherever you want. It's centered along where the screen was, so if you just.
Oh, there's a timeline, that's.
And we'll do a little. Oh, perfect. All the time, fond of care, so.
There used to be like a big chat.
There used to be, yes.
Oh, yeah. If I want to write it down, I think.
Larger.
Right, okay,
Yeah. So you reserve the.
Larger. You're good to do it. I don't know.
Oh, is it true?
Sort of right.
We could also bring the interaction usually.
I don't know how to make this refocus. It's supposed to be dynamic.
Ah, that works.
That actually helped. Okay.
Oh, thanks.
So go ahead and, I'll just also read it and each, we'll give a short introduction as to what you guys work on. Okay, so, thanks for sticking around, Sarah. Audience members who are still present in our remote audience, we're going to get started with our panel Q&A here. Very good. Nice and so, just a reminder of how this all goes. Obviously, we're here in person, but we're broadcasting to YouTube and Facebook and Twitter. And we have panelists who are graduate students and postdocs who work in the field of astronomy and astrophysics, who work on different aspects of science, who are here to field questions from you on whatever's on your mind and related to space science. So we have, I don't know how well you guys can read this. This is the first time we're drawing this setup, so hopefully it's somewhat visible. But behind each of our panelists, there's their name and then a couple of topics that they feel comfortable answering questions on because it's related to their research or past research or something like that. So, Isabel, since you're leftmost, you want to start out and just say like who you are and maybe give like 30 seconds of what sort of science you work on. So,
Yeah. All right. Hi, I'm Isabel. I am a first-year physics PhD student. My background is kind of really in theoretical and computational cosmology and astrophysics. So I primarily work on simulations of large-scale structure in the universe.
Perfect.
I guess I'm next. Hi everybody, I'm Dylan. I am also a grad student, and I work primarily on radio astronomy, and in particular using radio telescopes to detect explosions at various times, including supernovae.
Hi everyone, I'm Gina. I'm a postdoc, and I work on observations to study the formation of stars and other ways of going to measure things like distances in the universe.
I am Stephanie, and I am a recovering academic, and by which I mean I have my PhD and now I'm studying communication as a full-time job, but when I did do research, I studied the solar system and the asteroids and comets that will get out beyond that too.
Cool, sorry. Well, do you have any
Oh, I'm
questions?
wrong. So I have a physics question. So, you know, it is said that the electromagnetic force is communicated by photon.
Wait. You should do this, because it sounds like it's a long question first.
Yeah, so, it is said that the electromagnetic force is carried by photons, right? So how does that work in electrostatics? Like, for example, if you have two threads close to each other, or we're having some positive, you know, spheres, positively charged, and they're separated a little bit, right? So why are the photons there? Am I missing something?
Who wants to take this?
I can try to answer it. I just took quantum field theory, which is kind of the answer. So technically there are processes that happen with individual particles interacting with each other, and that's where the photon is kind of exchanged. If you've ever seen a Feynman diagram, that's kind of best depicting. It's called quantum electrodynamics. But for the purposes of most electrostatics problems, you don't need to do that. If that makes sense.
So the answer is that it is not necessarily true.
I mean,
Photons are exchanged.
it happens, but it's just, I think a good analogy is like how Newton's gravitational law works for certain problems on a classical scale. Like if you have to, like, you can get things to a certain level of accuracy, but if you want a tiny bit of extra precision, then you need to use general relativity. This is similar, except for it's quantum. Instead of using classical electrostatics, you would have to use quantum electrodynamics.
There's a video by Veritasium, you know, the Veritasium on YouTube.
That is correct, right?
Veritasium. So the video is called How Electricity Works, and he answers this exact question with beautiful graphics. It's like at school you learn about Ohm's law and how in a circuit but there's actually a field that he develops in the circuitry. You can understand that with interactions of photons, but it's just too complicated for most textbooks to explain. But this video does a great job of connecting one to the other. How electricity works.
There's a question.
So there's a question from our online audience, which is, what discoveries can be expected to be made by the James Webb Space Telescope in general, but also specifically about in relation to gravitational waves emerging neutron stars after being able to view them in the infrared. So I guess it's multi-part. It's both about the content of the presentation as well as just in general, what sort of discoveries is James Webb going to be making when it starts returning results in the next month or two. Anybody wants it?
I can take a crack at it. Yeah, so James Webb is going to be a super multi-purpose telescope. You might have heard that it's the successor to Hubble, but it's also looking at a slightly redder wave, looking in the infrared. And so that actually happens to be where some of the brightest emission from neutron star emergers, the brightest electromagnetic emission from neutron star emergers is coming out. And so James Webb will give you unprecedented sensitivity to detect extremely faint counterparts if they're there to some of these gravitational wave mergers. In the case of neutron star mergers, I think we're more likely to be limited by the sensitivity of the gravitational wave detectors. So James Webb will be a little bit overkill when it comes to detecting the macrowaves, but we'll get it in amazing detail, and also we'll be able to get really, really high resolution spectra, which can tell you about the chemical composition of some of the elements being synthesized in these mergers. You might have heard gold, for example, is made in neutron star mergers. We'll probably learn a lot more about it in the process.
I'll just add that another important consideration for any space-based telescope is they have a limited amount of fuel. And so it's not like we'll be able to just point JWST wherever we find one of these things. It's really going to be more like hopefully it's pointing in the right place at the right time. It's not going to be a follow-up observational instrument, but if it's in the field of view, then we'll see it.
Thank you. There's another question, I guess, related to the content of the presentation, and that is, do we have estimates as to the ratio of the number of neutron stars in the universe relative to the number of black holes? Seems like stellar evolution might allow us to do that, but maybe I'm mistaken.
Yeah, so it's probably.
Yeah.
No, that's smart.
Sure.
That'll be fine. That'll be
It's good.
Oh,
It's hard- it's hard.
Okay, yes, so they're not 100%, very precise estimates, but from what we can observe, we can estimate things like how many neutron stars collide in the universe versus how many black holes collide in the universe. And there's about 10 times or more neutron stars and black holes colliding in the universe. But what is interesting is that even though there's more neutron stars colliding in the universe, we actually observe more black holes colliding in the universe, and that's because we're more sensitive to them. The gravitational wave observatories are a gravity experiment, which means we're more sensitive to more massive things, and black holes are many times more massive than neutron stars. So the signals we emit are stronger, so we can see them further out in the universe. So we actually observed something like 20 to 1 to 30 to 1, no, more. We observed about 100 black hole mergers and only a couple of neutron star collisions. So 150, 140, let's say, ratio. But this is what we observe because we are very sensitive to black holes, but there are way more neutron stars than black holes out there.
Thank you, Katerina. There's a question here about the Sagittarius A star result. So there was a big announcement yesterday about this new image that was taken of the supermassive black hole in the center of our own galaxy. That black hole is called Sagittarius A star, and the team, the EHT team, the Event Horizon Telescope, was able to take an image of it. And I forget the exact ratio. Perhaps one of the other members can get it. But it was something like being able to see something at the distance of the moon that's the size of the thing. Yes. So it's a very, very small angular size relative to our position here on the Earth. But the question is, the image of Sagittarius A star is tremendous. How is the radio telescope focused to make sure it is getting data from the correct object and not perhaps something in the background or something in the foreground or whatnot? I guess we don't have any radio. Well, you're a radio astronomer. Well, you get to answer the question.
All right, I've been voluntold. Okay. So radio telescopes work a little bit different than optical telescopes. There really isn't a concept of focusing as much. So the way you get this incredible resolution from radio telescopes is you're actually combining signals, in the case of the Event Horizon Telescope, from opposite sides of the world. So the Event Horizon Telescope has stations all around the world. And essentially what you're doing is you're trying to simulate a telescope that's basically the size of Earth. Imagine you have a mirror. So the fineness of your resolution in pretty much any telescope is going to scale with the size of your telescope. If your telescope is bigger, then your resolution is going to be better. And in the case of a radio telescope, you can imagine you have like patches of a mirror, just like one little bit of glass, maybe in England, and then another bit of glass at the South Pole. And you're combining the signals from those little patches, and you're trying to synthesize what you would see from if you had patches of glass everywhere in between, like in the middle of the Atlantic Ocean. And so there's a lot of complicated math that goes into combining these signals. One thing that you can imagine is one of the most important things to measure is the time delay of light arriving at one telescope on one part of the Earth compared to another telescope on another part. So, you're going to get light a little bit sooner in one part of the Earth than you are in another. And that information you can piece together to synthesize this image with this incredible resolution.
I just want to add another plug for Veritasium. He made another. I think this is apparently the Veritasium promo show. But he released a video yesterday that also does a really great job of explaining this exact concept. I really encourage you to watch that video.
Oh, cool.
Excellent. There's a question here. Have we ever observed a new star ignite? Like actually just, well, yeah, I'll let somebody who's more capable talk about formation of stars and what that means, but starting nuclear fusion ignition in its core, have we seen that happen, or can we infer that that's happening? Star formation.
So I think the answer is no. I will tell you why I think the answer is no. And if yes, you will get it correct. So I think the answer is no, because we know that young stars are born inside very dense environments. They're enveloped in like a belly of, for lack of a better analogy, of dust, which obscures our view to them. So even if they ignite, we have to wait a little bit until all that dust clears up to be able to see it. There's actually I think it's called the first core. That's the terminology that we use. That is, in this embedded thing that is the young star, the first object, the youngest object that is starting to fuse. That's what they use for it, but I don't think we've observed other additions.
Yeah, so I guess one thing that I'll say is that it's not like an instantaneous event, a star igniting. It actually takes quite a long time for the gas to collapse. And for, there is at some point going to be the first nuclear fusion reaction at the center when the temperature reaches the temperature, but the light coming out from that nuclear fusion reaction, the energy, probably is going to take quite a long time to diffuse out and escape the surface of all the gas that's collapsing. I don't know what it is for a really young star, maybe somebody else does. The number of they have on the head is that even in the sun, the photons coming out of nuclear fusion reactions take like 1 million years to reach the surface. And so we're not going to like see it, boom, flash. But we have observed really young stars in many different stages of formation, including in the initial stages of collapse. There's this whole field of like protostars. Okay.
Thanks, guys. That was great. I think people can still hear me. Stephen Schreier asks, is there any instrumentation that can detect stellar mass black holes that don't have accretion disks? Because oftentimes that's how we detect it. He's thinking particularly of future Star Trek space travelers trying to avoid black holes as they fly through space. Is there the technology to detect these black holes in any way?
So if the black hole is in a binary, we can detect it with gravitational waves. Unfortunately, a black hole on its own sitting there, or even traveling, you are not going to realize it's there until it's probably too late. Because it doesn't really emit anything. Unless there's matter around it, so the accretion disk, it's not going to emit any light. Unless there's another big object around like another black hole, it's not going to emit strong gravitational waves either. You'll figure out when you get close enough to it, but then depends on how good your spaceship is for evading.
Yeah, like Katerina was saying, you can't directly detect it, but there are indirect ways that you can potentially figure out that there's a black hole. There's actually like probably millions or maybe even billions of black holes floating around the galaxy. We just don't know about most of them. But there have been some detections from this process called microlensing, where the black hole just happens to pass in front of a star, and you see the light from the star bend ever so slightly. You can detect that as the star getting bright in a very particular shape, and so you can kind of infer that there's a black hole in there. But like I don't know, so you can't actually see the black hole directly.
Okay, thank you guys. Let's see, looking for other questions. I think the weird delay kind of used up some of our audience. This is a question from Jirish Ananda related to the presentation, suggesting are concepts of Bose-Einstein condensates applicable in the case of very high temperature cores in stars or in neutron stars, since gravity holds the particles together in the core. And maybe it's worthwhile to just introduce what a Bose-Einstein condensate is or roughly speaking, since many of the audience members might not understand that phase of matter.
Yeah, so right. So as you go to the center of the star, like I said, you kind of start losing complete track of what matter behaves like, and that has led to a lot of theories and ideas for how matter could behave. And there are even ideas that suggest that maybe neutron stars have no neutrons at all. So I don't know, we still call them neutron stars. Actually, we don't, we call them strange stars. But they look very similar to neutron stars. Sometimes we just get lazy and call them neutron stars. So there are a lot of speculative ideas for what could potentially happen based on known interactions between elementary or non-elementary particles, based on known interactions, how those interactions could be arranged in a way to create so much pressure to support an object that is so massive yet so small. So yes, all those things have been proposed and explored, and I would say there are definitely theories and ideas and calculations for how the signal would look like. Ultimately, we have to rely on some sort of observational verification of all of those. And this is what we can potentially do, and we're trying to do both gravitational waves and electromagnetic. But at the core of the problem is that we have to come up with some sort of matter that creates enough pressure to support those stars, and we still don't fully know how to actually do this calculation. So all sort of exotic possibilities could come up. I mean, one idea is the cores of neutron stars are just dark matter. The dark matter goes inside the neutron stars and accumulates there, and their cores are made of dark matter. It's possible. I would say likely. It's possible. Yeah.
Very interesting. Oh, I don't know if this is.
Yeah.
Oh, yeah, sure. That microphone's probably well here.
So you have the temperature limit for black holes. Do you have something similar for neutron stars?
You mean for white dwarfs?
For white dwarfs?
Yes. Yes.
And how do you calculate that?
This is actually quite an interesting story. So for white dwarfs, white dwarfs are supported by what we call electron degeneracy pressure, which is interaction between electrons. And the Chatziioannou limit says that their mass cannot be above something like 1.4 square. For neutron stars, if you do the similar calculation, now neutron stars, instead of electron pressure, are supported by neutron pressure. That's why they're called neutron stars, by the way. And because they're made of neutrons, they're made of a lot of stuff.
but they're supported by interaction between neutrons. This is the canonical idea. So if you do this calculation for neutron stars and say what's the largest they can possibly be, the answer is about 0.8 solar masses, which is extremely low and extremely wrong. Because we have seen neutron stars way more massive than this. There's something else going on. And what else is going on is that there are also additional nuclear interactions that go beyond normal neutron degeneracy pressure that allow you to increase the mass to what we usually observe, which is 1.4, maybe 2 times the mass of the sun. But you can keep pushing this sort of exercise and say, can I derive a standard Chandrasekhar-like limit, not directly coming from neutron degeneracy pressure, but nuclear interactions in general. And that limit is actually 3.2 solar masses. This is the strongest pressure can be such that it obeys common physical laws. And the most common physical law that comes into play here is causality, which means that nothing can travel faster than the speed of light. So interactions within the neutron stars described by the speed of sound, actually. The speed of sound cannot be larger than the speed of light inside a neutron star. The absolute upper limit is 3.2 solar masses. So that would be your equivalent to a Chandrasekhar mass, but derived slightly different.
Very interesting. I learned something too. There is a question from Wei Sensei asking, would the infalling of a planet into a star also release gravitational waves in theory, but just too weak for us to detect currently with our technology today?
Yes, yes, it would. I mean, in theory, the Earth going around the sun emits gravitational waves, or I don't know, Mercury going around the sun, but they're too weak. Your standard back of the envelope calculation said that unless you have something like a black hole or a neutron star or a white dwarf, something extremely massive, the waves are too high to be detected.
Okay. I think we burned through most of the questions. Yeah, okay, yeah, by all means.
Should I change my voice? So, you have, white dwarfs, then you have neutron stars, getting heavier and heavier, denser and denser, black holes. You have something in the middle, like where, because there is some empty space in white dwarfs, right? Between the electrons and the nuclei, right? And that kind of goes away. In a neutron star, and kind of further goes away somewhere. So, is there some empty space in a neutron star as well? So, can we have a quark star, for example?
Yeah. So this is one of the exotic ideas for what would happen. So basically, if you have, if you keep increasing the density, you get to the point where neutrons get so close together that the quarks are not assigned to a specific neutron; they're just all over the place. So you basically have like a soup of quarks, and you can have. There are theories where you can have either this happening at the center, just at the center of the star, while the outer layers are more normal neutron matter. All this could be happening in the entire star. So that's the sort of situation where, can you really call it a neutron star anymore? Probably not. It's a quark star or something like that. But yes, the problem with this kind of objects is that it's not easy to make the much observations. So what we definitely know that not all of the stars we see out there that look like neutron stars are quark stars. You might have some. It is possible that you have some, but the majority of what we're seeing have to be neutron stars in the more traditional sense of the word. Yeah.
Or you're basically saying that the core might be quark, but you may not be able to see it. The outside is not that. Is that what you're saying?
Sorry.
Quark. So what are you saying that the core of a neutron star might actually be quark too, but the outside won't be because there isn't that much pressure in there.
Exactly. So as you go inside, what matter looks like changes. Like same way in the Earth, the core, the surface look the same.
Okay.
Okay, there's one last question, I think, and that is, can the Event Horizon Telescope, the one that was responsible for taking these images of the supermassive black hole in the center of our galaxy, can it also capture images of nearby neutron stars, other smallish structures? And thanks for the wonderful presentation this evening. So the EHT is as Dylan was discussing earlier, is a radio telescope. So it images things through radio emission from distant sources. So do we expect there to be a significant radio emission source around neutron stars?
Yeah, so the pulses that neutron stars emit are the majority are in radio. So neutron stars emit almost all wavelengths, basically. But the pulses that we see, this light pulse effect that is right, is actually in radio. So that's how we typically detect them. Imaging, I would probably, my guess is they would be too small, so we wouldn't have the angular resolution to actually do this. You can do optical imaging because they're cold, they don't emit much, most of them. But with radio resolution, they're probably smaller than a donut on the
Yeah.
on the sun, on the sky, so it would be too small to see.
Yeah, I think you're right.
They're 10 kilometers wide.
In physical size,
So,
yeah.
yeah, actually, like the radius, let's say 20 kilometers in diameter.
Yeah.
They're smaller than the Chatziioannou star. Even though we kept saying about the press announcement kept saying it's a Chatziioannou star is small as far as like what their galaxy are concerned, it's still bigger than 10 kilometers.
Yeah. Okay, well, yeah, I'd like to thank all of our panelists for helping out tonight. Yeah, much applause, thank you. And thank you to our speaker again, Katerina. And thanks, audience members, for coming out and joining us tonight, either in person or online. And our next event will be a month from now. As I said, there will be a presentation given. I'm planning to do it hybrid as well, in person. I mean, maybe we'll just do the in-person and then record this and put it out there and not live stream it. I don't know. Maybe we'll get more people to show up in person. And our next Astronomy on Tap is a week from this coming Monday on the science of Star Trek and the science of Star Wars. It will not be online. It won't be in person yet. It'll be online, but I'll have the announcement up for that soon. So thanks everybody for joining us.
Thank you.